Plain text processing in structured documents. My name is NicoVerwer. I work as an independent consultant for my company Rakensi in the Netherlands. In this talk, we will look at how to apply natural language processing or other text processing algorithms to XML documents. The problem is that most of these text processing algorithms work on plain text. But XML documents, of course, are not just plain text. They also contain structure or markup. Also, these algorithms often recognize pieces of text or add annotations to pieces of text or other information. And then we want to add that to the original XML document. Examples are phrase recognition, but also sentiment analysis or topic extraction. And these applications could all benefit from the techniques described in this talk. The work that I described was done in the context of the link extractor. The link extractor is an application that detects and resolves references to legislation, case law, and other governmental and legal documents. And it was developed for the Expert Center for Official Governmental Publications, called COPE in the Netherlands. The work was done under the supervision of Mark van Alpijne, who I wish to thank for providing the opportunity to work on all this. So what does the link extractor do? It detects references which are pieces of text, not necessarily contiguous pieces of text, and then it marks them by putting XML elements around them, and when possible, it will also provide a link to the document that's referred to. In the example here, there's a piece of text, the opinion of the Advocate General for the judgment of the European Court of Justice of the 22nd of April 1997, followed by a case number. And the link extractor has inserted two links with a ref element referring to an ECLI, or European Case Law Identifier. This is basically what it does, and in order to recognize pieces of text, the link extractor uses two different algorithms. The first is named entity recognition. Named entities are fixed pieces of text that represent an entity in the real world. For instance, in the link extractor, we have titles and abbreviations of laws. We have applicants and case names for the European Court for Human Rights, and we have case law aliases. And altogether, there are more than 350,000 of these named entities, which we must recognize. We use a structure called a tree to do this efficiently. A tree, the name comes from retrieval and from tree, because in memory it's a tree like the one behind me. And this named entity recognition tree matcher scans plain text. There's no XML it can recognize. And I've done it in such a way that I can mark the named entities as XML elements. Apart from this, there's some normalization going on for upper and lower case, for accents that may or may not be present in the text, and different Unicode representations for things like dashes or quote marks. The other algorithm used by the link extractor are parsing expression grammars. Parsing expression grammars are a bit like regular expressions, but with named sub-expressions, which means you can give a parsing expression a name and use it in another parsing expression. It's like subroutines for regular expressions. Alternatively, you can view a parsing expression grammar as a context-free grammar, but the parser generated for it can efficiently solve ambiguities without having to use backtracking. This means that it's quite efficient both in memory and in CPU time, like the named entity recognizer using trees. An example you can see here. This is the rule for element number, And there are several references to other non-terminals, as they're called, like regeling or SP for space. They're all marked in yellow, and those refer to other rules in the same grammar. For the link extractor, we have used the WXI parsing generator, which generates pretty efficient parsers, but they can only parse plain text, no XML. And the result is a parse tree. Now, since that's a tree structure and XML also is a way of representing trees, it's quite easy to represent this parse tree in XML, which is what we do indeed. So now we can recognize pieces of text and combine them using these grammars. But how are we going to add markup to the document? Here again, I have a part of a document above, and in the lowest bullet points, we have recognized several things like Supreme Court, which is a named entity, and it's marked by Alex instantie, which is a Dutch term for things like Supreme Courts and other courts of law. We've recognized the date, and there have been many other things recognized which I haven't shown the markup for. That would become too big. But in the end, we want to put a link element around this. And that's the link element you can see over there. And the end is after the case number over there. But the start is just before the Alex instantie element. And now we have a problem because the start tag of the link is right in the middle of the M element that was already present in the input document. So if we would put a start tag within the M element and an end tag at the end of the link, that would not be a well-formed XML document. Actually, it wouldn't be an XML document at all anymore. So we can't do this. So we have strategies to deal with this, which I will speak about later. And then when you have thought of these strategies, the question is, how can this be implemented? Now, very first version of the link extractor was made in C#. It could have been made in Java. It used regular expressions. But it quickly became very complicated and unmaintainable. And that's, of course, because Java and C# are not declarative programming methods. You have to prescribe to the computer how it has to do every little action. So we don't want that. So then you could think, maybe I'll use one or more XSLTs for this. Now, of course, named entity recognition and with trees and peg parsing are not part of XSLT, but we could easily make Java extension functions for Saxon and include those. But it still would not really be easy to fix problems like how to get just the text for parsing a piece of text whilst maintaining the structure, the XML elements in that text. So what we did, we made a pipeline of 70 with more, I think, XSLT and Java components, and named entity recognition and peg parsers are written in Java, but then there are operations for disambiguation or text normalization that are made in XSLT. Also, the reference construction and link resolution, finding the link to the referred document, are done using XSLT and some Java components. So all this leads to a lot of accidental complexity, and here's an example of why that happens. Suppose we have a piece of text where the named entity recognizer has recognized the string EG, which is Dutch for European Union, EU, and it's also an abbreviation for regeling or regulation. In this case, it's a treaty. But it's also part of the reference that's given next, which means that when parsing legal references or complete references to regulations, we have to deal with this embedded markup of the Alex regeling element. since our peg parser can only process plain text, we will have to serialize this text coming out of the XML coming out of the named entity recognition. So we've serialized XML, but now our grammar must take this into account. So up here is the grammar we use. For regeling, we first recognize a regeling start, then that green stuff, that is the actual thing we want to recognize, and then we have the Alex regeling end. And then there are two rules here, one for the regeling start and the regeling end. And as you can see, these are really small XML parser. Now, of course, an XML parser is not really part of how to recognize a reference to regulations. And since the grammars have to be maintainable by domain experts who know all about how references are made in text, we have a problem here because we've added complexity, accidental complexity, which is there not because of the recognition task, but because of a specific technical solution that we had to choose. So for the maintainer of these grammars, this is a very undesirable situation because now they have to deal with extra complexity that has nothing to do with their actual task. It's even worse because when the peg parser has done its work, this is what it will produce over here. And you can see that this includes the parse tree for all this extra stuff that we had to add to the grammar. So we have Alex regeling element, but also the regeling start. Then we have the serialized version of that Alex regeling element. And then we have the end of the regeling start. Then we have EG, etc., etc. It's even too much to fit on this slide. So in order to solve that, after every parsing step, we have to add a normalization step to make this into something that looks like the original again. And that also means that the programmer for this has to deal with accidental complexity, which makes the task of putting a link extractor together much more complicated. So how can we solve this? Well, we developed SMAX, the Separated Markup API for XML. And using this API, it's possible to process the text content of an XML document as a linear string or stream of characters without any intervening markup. But at the same time, SMAX retains and allows you to modify the structure and markup of the document. How it does this is by keeping the markup, the structure of the document, and the text content separate. So it stores them separately. The content is just one long string or stream of characters. And then somewhere else, there's the markup tree, which does not contain any text content, but it does contain for every XML element the start and the end position in the linear text up here. So that means, for instance, we have this node containing the characters V, W, and X. And in the node itself, up in the tree there, it has recorded that the start position is 21 and the end position is 24. If we do this for every node in the tree, every XML element, it's possible to later turn this into a DOM or a SAX representation quite easily. Also, we have to assign the start and end positions in such a way that the tree is balanced or that we have a well-formed XML document. So these character positions up here, they should be properly contained within the positions of their parent, and they should not overlap with the character positions of their siblings. So what happens when we insert an element? Well, on the left, there's a yellow element containing the text H, I, J, K. And if we insert that, it perfectly fits in its parent. So we can just keep its start and end position and all is well. However, in the second case, we have a node that spans the text STUV. And now the question is, where do we insert this? Because the start position is within the node that's up there on the second row, but the end position is within a node in the third row that's lower. And that will lead to non-well-formed XML. So in order to deal with this, we've developed several what's called balancing strategies to make the tree well-formed again. These balancing strategies make sure that whenever we insert an element, the well-formedness of the markup tree is preserved. And also, if we create other operations on nodes in the XML tree, this must also be guaranteed. We have 6 balancing strategies. 4 of them are only needed for unbalanced insertions. So when we use that strategy on a balanced insertion, everything will be the same as it was before. And then we have 2 strategies that are mainly used for balanced insertions and that have the same effect, start and end, as the balanced start and balanced to end strategies. I will describe these strategies next. The details are in the paper that will be in the conference proceedings. So I will not go into every possible detail here. First, let's look at what happens when we have well-formed or balanced insertion. And here we want to insert a new element M with start and end positions that lead to a balanced tree, so no balancing is actually needed. And you can see that here in the first row, M contains 1 or more XML elements. In this case, it's P, R, and Q. And if we insert it with the outer-inner balance to start or balance to end strategies, it will just contain the elements P, R, and Q. And M will be inserted in the parent of P, R, and Q at the position where P, R, and Q used to be. If M in second row is inserted between 2 elements but doesn't contain any existing elements, it's just inserted at the place where we want to insert it. And when M is inserted into one element P, that's the lower row, then we insert it recursively. So we'll see what happens with the children of P. So the insertion procedure, the insertion method is called recursively. The start strategy and end strategy both collapse M to its start or end position. So let's have a look at start. Here M is collapsed to the start. It's made an empty element and it's inserted before P in the top row. In the second row, it's inserted between P and Q, but at the start position of M. And when it's inserted in P in the third row, it's just inserted recursively, but at the start position. The end position does almost the same. It collapses M, but then to the end position. So then we have an empty element that occurs at the end position of M, which is inserted after Q in the top row. It's inserted just before Q in the second row, and it's recursively inserted into P in the third row. What happens when we have a non-well-formed or an unbalanced insertion? Well, there are several ways in which this can occur, and they all happen when the start or the end position of M falls within an existing element, but the other end or start position does not fall within the same element. Here I look at 2 of the possible strategies, outer and inner. And in the top row, the start position of M is inside the element P, but the end position of M is inside a different element Q. So if we use the outer balancing strategy, then M will be expanded to contain both P and Q. So that means not only does it now contain P, R, and Q, where R is the markup between P and Q, but it will also contain the content within P and Q. So the content has to change, content of M. If we use the inner strategy, then we shrink M so that it fits right in between P and Q. So the start position of M will be the end position of P, and the end position of M will be the start position of Q, and M fully contains R. And this means it could lose some, the element M could lose some of its content. We'll see that later. The second and the third row are the cases where only the start or the end position of M intersects with an existing element. So using the outer balancing strategy, M will be expanded either on the left side or the right side, and in the inner balancing strategy, M will be shrunk on the left side or the right side according to where M intersects with an existing element. So that's illustrated here. There are more strategies for unbalanced insertion. Start and balance to start are the same in this case, because balance to start is only used when there's an unbalanced insertion, and then it will use the start strategy. And end, balance to end, do the same for the end strategy. So in the first case, M intersects at its start position with P, it intersects its end position with Q, and as we saw earlier in the start and end strategies, M will be collapsed to either its start or end position. So it's not too difficult to see what happens here. If we use start or balance to start strategy, M will be made empty, an empty element, and it's inserted at its start position, which by definition always is within one element. In the first case, that's inside P when you use start, and in the end strategy, M is now fully contained in Q because we've collapsed to the end position. It's very similar for the other cases where M only cuts across an existing element at either the start or the end position. It's collapsed to the start or end position and inserted at that position in the tree. So this may be a bit abstract, so let's have a look at what this looks like in an actual XML document. Here we have a recognizer for one or more exclamation marks, and we want to surround these exclamation marks, mark them with an M element. So in the top row of well-formed insertions, the three, in this case, exclamation marks are contained within P, and we just put the M element around it, around the three exclamation marks. The start and the end strategies just make an empty element M, and they put it before the three exclamation marks or behind the three exclamation marks. In the second row, we have recognized exclamation marks, but there is intervening markup that's between the exclamation marks. And that means that this markup, because it's a well-formed insertion, will be absorbed by the new element M. And that's the same for the outer and the inner strategies, because the start and end position of M do not change. It will now just contain the exclamation marks plus the P and Q elements. And again, the start and end strategies are quite simple. We make an empty element M and put it either in front of the first exclamation mark or at the end of the last exclamation mark. In the third row, we have the case where there is some content surrounding the three exclamation marks, but they fall in between the P and Q elements. And in this case, again, we can just put the new element M around the three exclamation marks, or in front of the exclamation marks for start, or behind it in case of end. That was easy, but let's look at some non-well-formed insertions. In the top row, we have the case where the start of the new element M is inside the element P, and the end position of the new element M is inside Q. So clearly we can't insert M there, and here the outer and inner balancing strategies are different. So first look at the outer balancing strategy, and there we see that up there somewhere, that M now contains both P and Q and the content that was inside P and Q, apart from the exclamation mark. So that's two red dots that are there. So M has been expanded to contain more than it was meant to contain. For the inner balancing strategy, we shrink M so that it fits between P and Q, but that means it also loses some of the content, the exclamation marks, that was recognized. So there's a clear difference now between the outer and inner balancing strategies. If we use the start and balance to start strategy, it's very simple because M is again collapsed to an empty element, and we just put it in front of the first exclamation mark up there, and now M will be fully contained within the element P. The second row and the third row show the cases where M intersects with an existing element only at the start or the end position. Apart from that, it's all very similar. When we use the outer strategy, M is expanded either to the left or the right. And when we use the inner strategy, M is shrunk so that it does not intersect P or Q anymore, but it loses some of its contents. This is all described in detail in the paper, as I said. So if this was a bit hard to follow, that's understood. You can read it back in the proceedings. So now suppose that we have made a text processing component that uses SMAX. How can we use this in an actual application? For that, we have developed SPEAT, Simple Pipelines of Event API Transformers. As you probably have seen before, XML document processing is often done using pipelines. And there are technologies for this like XProc, Apache Cocoon, and several others. SPEAT is a Java library also for building pipelines from event APIs like SMAX and also SAX. So both SAX and SMAX are examples of event APIs where XML documents are represented by a series of events that are processed by an API. And each step in a SPEAT pipeline is going to be a transformer from one event API type to another event API type. So what does this look like? It's a bit like this. Here we have, we start with a serialized XML document, which is parsed by a SAX parser, producing SAX events. And you can see them over there. It's start document, followed by start element for the root element, then a lot of other events, and then finally we have an end element and an end document event. And as you can see, these are just method calls in the SAX API, which are then processed by the SAX to SMAX adapter, which takes SAX events and produces SMAX events. Now there's for each document just one SMAX event, which is process. And it takes one whole SMAX document, and the SMAX document has a separate part for the markup tree and for the text content of the XML document. We want to have that in one go because most of the text processing algorithms work on a full piece of text. So that means we have to have the full text of the document and all the markup. How this is represented in memory can be a string. It could also be a text stream to make things fit in memory. After some SMAX transformers, we end up with different SMAX. That's up there somewhere. And then we can transform that back into SAX, which can be serialized to produce a serialized XML document. So that's what a pipeline looks like. And now I'll say a few things about event API transformers. An event API is a way of representing events by method calls. And this is very efficient because method calls are already available in Java or almost all other programming languages. And it's very easy to make a processing component for that because you just have to implement the interface of all these methods to handle the events. It's much more efficient than making new objects for each event, which some APIs also do. But that's basically making a reification of the method call because it contains exactly the same information as the method call. But you have to make a new event object for every event, which is inefficient. And as I've shown in an earlier talk today, reification is usually not such a very good idea. So that's why I really like event API transformers. Now here I've also shown what a pipeline from S events to T events looks like. This is the Java interface declaration. And it extends event handler of S and event supplier of T, which means that S events are the input and T events are the output of this pipeline from S to T. There's a technical reason why event handler and event supplier are needed, and that's because Java does not support covariance and contravariance of type parameters. This is a rather technical issue. If you don't know about this, it's worth reading about it, I think. And people who use C# do have covariance and contravariance, and then S would be an in type parameter and T would be an out type parameter. That's why we have that. And here you can also see that one S event up there resulting from a method call can result in more than one T event being output by this pipeline from S to T. Also, not every S event will result in one T event. There's no one-to-one correspondence. So you can collect a few S events and then produce one T event after a while. So this is also quite powerful. The correspondence between S and T events is not one-to-one, which makes this a very versatile way of handling events. Now this is what a pipeline looks in code. What it looks like in code. So here we have a SMAX document transformer NER, which is a named entity recognizer, which uses a grammar source, which is an input source. In this case, as you can see up there, it's a string input source. And that's because this is part of one of the unit tests that I've made for SPEAT and SMAX. It has some other parameters. We can set some attributes like case insensitive min length, match node template, which is an XML template that is inserted for every recognized named entity. And then we set the balancing strategy to outer. We make a SAX reader that reads SAX events. It has an input source. There's a SAX writer that can output SAX events. And then that also has an output property. It will output an XML declaration. And then we can create a pipeline. So we have the SAX reader. We append the SAX to SMAX adapter. We append the named entity recognizer, append a SMAX to SAX adapter, and then append the SAX writer. And that forms a complete pipeline, which actually works because, as I said, this is one of the unit tests. So what are these unit tests? Well, I've made SPEAT and SMAX open source this week. You can see the GitHub URL up there. Most of the code is available as open source. Some pipeline components are available, but not all that we've developed for the link extractor, because some of the code is proprietary for the Expert Center for Governmental Publications. Maybe at one point they'll decide that that can be open sourced. There's an adapter for SPEAT pipelines in Apache Cocoon, because we originally made the link extractor in Apache Cocoon. And I would really like to make an adapter for SPEAT for one or both Xproc 3 implementations. I'm sorry for the spelling mistake in Xproc. I think the P should be capitalized. So this is open source. It's not meant to be a framework. SPEAT and SMAX are a Java library which can be used from within another framework like Apache Cocoon or Xproc 3 or anything else that you like to use it within. And I intend to keep it that way because there are already lots of frameworks for XML processing, and this is meant to be an addition if you need to process just the text of a document without looking at the markup structure. So that's it. There's some time for questions left. Thank you for your attention.